Welcome to the first video for buckling. In this one we'll go through just the basic idea of buckling and what that does. So far, when we've considered our load limits for structures, we've only considered the stress as far as the material is concerned. So just the force over the area that will cause the material to either fracture or yield or crush. So we limit our stress to be below some allowable stress. We might also have some maximum deflection. So in that case, we would limit our force P by maybe something like L over AE. Say that the deflection has to be less than or equal to some allowable deflection. But this is only some of the ways that things can fail. If things are, if things break, sure, they failed, as well as if things deflect too much to be usable. There's another way that things in compression can fail, and that is if we have a column, and let's say it's pinned, and we apply some loads to it, it can buckle out. So, well, it doesn't necessarily have to be pinned, but it sure makes for a nicer drawing. This is a sudden release of the force that will cause a sudden failure in the column. So it's a particularly bad failure state. And it can only occur in compression elements. So it can be either in compression due to it being a column, experiencing an axial load, or it can be a compression portion of bending moment. Remember, part of something in pure bending is going to be experiencing compression. Those parts can buckle as well. And so it leads to these very sudden instabilities where it'll suddenly move laterally out of the way of the load, and it'll shed most of the load that it's holding. So it's a particularly sudden failure. As an example, let's consider this 2-bar linkage pinned on top and bottom, and with a pinned connection between the two. So this is not a pinned support, it's a hinge connection between the bars B, C, and A, C, with a hinge at C and a torsion spring right here, an elastic torsion spring. And we apply a force P at the top and a reaction at the bottom as well, so that we're not accelerating downward. If we're looking at this and we're applying some small deflection, I know I've drawn it to be a substantially large deflection, but it's a small one. Okay, if we do that, then we're going to have, as we force this down and force this out, this spring is going to exert a moment to try to push us back into straight up and down. So as we push out, the moment exerted by the spring is going to go up. The moment exerted by the spring, which I'm going to call M spring for fairly, I think, self-evident reasons, will be 2 times the spring constant times whatever this change in theta is, right? So as we change theta and increase it, we're going to have this moment be exerted down here by the spring. Now, we're also going to have a destabilizing moment. It'll be formed by this couple P right here. So this couple P is going to cause a moment in this direction, while our resisting spring is going to cause a moment in that direction of this. That is going to be equal to, and I'm going to call it destabilizing moment. And that is going to be equal to the force P times 1/2 of the length and times, it's just this distance, right? So 1/2 the length times the sine of whatever this angle theta is. Now, I said this was a small deflection, and I haven't drawn it that way, but it is, right? I just want to be able to see the angles. So this is going to just about equal, because we're going to have this be very small, so we'll be able to say that the sine of theta is approximately equal to theta. So then this will become P L halves theta. And a reminder here that if we're going to pull this trick, we do need to be using we need to be using radians and not degrees. So be careful with that when we do this trick. So as long as these are equal, or as long as the capacity for this spring is greater than or equal to the destabilizing moment, then it's stable. So it's stable. Let's write that out again, but with what these are. So 2 times k times the rotation theta has to be greater than or equal to this PL over 2 theta. If it is less than this destabilizing moment, then we are unstable. So just the exact same equation, but point it the other way. Oh, don't do that. Those of you who are actually really paying attention are probably going to note that this theta is on both sides. And what we really are going to want is we're really going to want this P all on its own, right? Because that'll give us the amount of force that we can apply before buckling begins. So if we rearrange this, and we could just divide theta out from this, we'll get that the critical load at which this becomes unstable is going to equal 4 times the stiffness of the spring divided by the length. So when we're looking at that, we're going to notice that it's a function of the length, it's a function of k, the stiffness of the spring, but it's not actually a function of the rotation. So as long as we have small rotation, as long as the deflection is small enough that we can sort of reasonably make this claim, then the critical force that is the point at which we reach bifurcation. That's when we stop being stable in this state and just pop outward, that's independent of the deflection, so long as the deflection is relatively small. So it's only a function of the length and the stiffness of the spring. And we're going to see when we look at more realistic columns that don't have torsion springs in them, we're going to see that holds true for a lot of for other portions of columns. For more reasonable columns, similar things are going to happen where the stiffness of the column is going to be affecting it, and the length of the column will be affecting it, but the deflection of the midpoints of the column are not going to be an issue until seldom they are. And so we'll look at those more realistic columns in the next video.